Okay, good morning. We can start the next lecture. Recall that we started to study something which is called Lie algebra. And we started to define it with no connection to Lie groups, just to study Lie algebras a little bit. And then we will go to the topics that how Lie algebras are inserted somehow in Lie groups, or how can they be computed from Lie groups. So still about general Lie algebras, and I also repeat, hopefully, that there is an appendix in the book which is called Lie algebras at the very end, and it is useful to read it. It is just 2 pages maximum, or 1 or 2 pages. So the definition, Lie algebra is a linear space usually finite dimensional, but we will see that not necessarily, and a new structure with respect to the linear space, some additional structure, is that one can make a commutator, so-called commutator of 2 elements, or Lie bracket. It is the same thing, and it is just some kind of multiplication which has properties, multiplication in the sense that you give me 2 elements and I return you a single one computed from these 2, some binary operation. And it has property that it is antisymmetric. It is bilinear. Yes, it is bilinear. It means that also with respect to the right slot. And third, that there is something called Jacobi identity. That iterated commutator plus 2 cyclic permutations is always 0 for any 3 elements. Now, does the structures like that exist in the nature? That can we have some example? Yes. First example was standard E3 and vector product. Yes, so the commutator, official commutator of 2 vectors, standard vectors from first year of physics, is by definition A cross B. So this is well known to be bilinear, skew symmetric, and what is not completely clear whether the Jacobi identity is fulfilled, but I told you that check and you will see, and the check is simple because we know that the formula in components reads AJBK. So from this formula and from standard work with epsilons, maybe deltas, I don't remember, you will check that Jacobi identity, that means vector product A cross B cross C plus cyclic permutations, really happens to be 0 for any 3 vectors. This is a nice example to learn how to compute vector products from the first year. Remember that maybe you have some examination when you had to compute this and recompute it to some other expression, but not very often is an exercise that compute this plus cyclic permutation to show that it is zero. Did you compute it sometimes before me or in the first year, or I mean including the cyclic permutation? Because it is not very useful. Yes, that's why it is not very much computed. So after checking that Jacobi identity really holds, we see that we have the first example of Lie algebra. Second example is actually a big class and very important, maybe the most important class of Lie algebra, are that first take associative algebra. That means we already know, because I think that we already used it. Did we have here in this lecture the concept of associative algebra? No? But well, did we have this concept or this notation somewhere in this lecture? It is the space of functions on a manifold. Maybe we already treated functions of manifold. It was already defined, but I didn't mention, so I can mention it here. Well, there is a gap, that if you have two functions on manifold, we already know what is it. We can make these constructions, which are called linear combination of two functions and a product, standard product. By this product, I mean that if you compute it at point n on manifold, by definition, it is FMGM. So whenever you see something like x cosine x plus tangent of x, it is doing these two operations. Here you have product of two functions. Here you have linear combination because the sum and so on. So we know that things like that happen in the universe, and they can be formalized that it is a linear combination of two functions, and this is a product, standard product. This is called pointwise product, that you compute it in the same point and then you multiply the numbers, the resulting numbers. Now, there is a concept of associative algebra that say it's called A. If we have two elements, we can do A plus lambda B. That means it is a linear space. And we can define AB, which is product. And this product should be associative. That means AB C equals A B C. So it doesn't matter how exactly you do which order you use for computing a triple product. That means that it is just ABC. Then, and if you now check this linear space with this product, you see, or you check that it is associative, this pointwise product. So the linear space of functions on any manifold give you an example of associative algebra. Yes, these 2 points of structure. And this product should be also bilinear. I1 plus lambda A2, A1, times B equals A1, B plus lambda A2B. So bilinear associative product in a linear space. First example, space of functions R-valued functions or C-valued functions. And second big example, matrices n by n. We know that whenever you have two matrices n by n, you can make linear combination, which is done by each element corresponding, the 1, 1 with 1, 1, and so on. And then we have matrix product. Yes, so we know that matrices can be linearly combined and multiplied, even non-square matrices, but square matrices are needed to give you consistency here. And so this is the second big example of the structure which is called associative algebra. It is also bilinear, this product, if you have a look by how it is done. And it is also associative. If you didn't realize it yet, so check that it is both associative product, bilinear product, and what, nothing more. So these two structures, well known, are nice examples that this structure is very important, that associative algebra is important because functions are important and matrices are important. There are also, of course, some other examples, but these two are already enough to realize that this is important structure for linear algebra. And now, let's start with some associative algebra, say matrices, and do a construction that define AB commutator by AB minus BA. This is okay operation in the associative algebra with the result in associative algebra. But now the claim is that this can be treated as a new product on the same set. And this new product creates a structure of Lie algebra. On each associative algebra, by this formula, you have another structure, the structure of Lie algebra. So the same set is at the same time also associative algebra and Lie algebra by this prescription. What should be checked? Is it bilinear? Because AB is bilinear, check that it is trivial, that it is bilinear. Yes, bilinearity is trivial. Skew symmetry is visible directly from construction. That if you reverse order BA, you will have minus the same expression. And what is a little bit non-trivial and should be checked is Jacobi identity again. But check that Jacobi identity also holds. It is a simple one-line computation. You write the left-hand side, then compute explicitly, and then you see that it is pairwise canceling everything, and you will finish with 0. So it is a very simple computation to check that this prescription really produces Lie algebra structure whenever you already have associative algebra structure. Sometimes it is not very interesting. For example, in this example number 1, this product has additional structure that Fg equals Gf directly from this formula, you see, because here is the product of real numbers, and real numbers have this property. This is not compulsory for associative algebra. It is specific feature of this Lie algebra, of this associative algebra. And if you have this specific feature that AB equals BA, then of course this is 0. So if you construct a commutator from associative algebra, which is in addition commutative, like that, you give nothing interesting. You give a commutator, which, by the way, check that it works, so to speak. That means that it obeys everything which Lie algebra should obey by definition, but it is trivial Lie algebra with zero commutator. It is a point which one can, well, come back and check that if you define xy equals 0 in some Lie algebra, it works. It is an official Lie algebra with zero commutator. Everything is satisfied. So here we obtain this kind of Lie algebra, not very deep, although it has some applications in physics and quite interesting. That trivial Lie algebra is that realize commutator in terms of 0 on the right-hand side. But if the product is not commutative, this gives you something non-zero, and then it is especially interesting. For example, the most important example for us is this guy, that matrices n by n are associative algebra, non-commutative, because multiplication of matrices more than 1 by 1 is non-commutative, and that's why this commutator is interesting, non-trivial. And we use it a lot. Actually, we restrict in this lecture, this semester, more or less to only to those Lie algebras. The structure, how it is done in the book, is different. In the book now we are in chapter 11, and we skipped some chapters, I don't know what, 3, 4, 5, 6, 7, and so on, because it is possible and may be useful also to introduce you to Lie algebras through matrices, because it is much simpler than via some other mechanism. And then, after studying more differential geometry, then you can learn in chapter 11 how it can be done officially, so to speak, using differential geometry on Lie groups. So the computation of Lie algebras for Lie groups will have some machinery here, which is based on the fact completely that our groups are composed of matrices. Then something quite simple exists, how to treat it. In the book is different strategy. First, learn some differential geometry, then apply it to Lie groups, which are manifolds, find something which is called left invariant vector fields, quite interesting objects, but not that simple for beginners, and then have a look that these left invariant vector fields produce some Lie algebra and call it Lie algebra of the group. Yes, so the strategy is to use different machinery, left invariant vector fields, and you can do the same, even more general. Then it is shown at the end of the chapter 11 that something that you can deduce our simple machinery from this more complicated machinery. Yes, and of course use it quite a lot. So now, because I more or less know what is in the book quite well, so I know that we can use directly point 11.7 in the book, not 11, 1, 2, 3, 4, and so on, because in 11.7 we just show that the work with matrices, in the case when they are there, is simpler. So why not use it from the very beginning? Because matrices have some limit. If you want to do something also interesting on Lie groups and with Lie algebras, it is better to use this differential geometry. Something is easier using differential geometry, and something is easier using matrices. Yes, so here on this lecture, I use the matrices first, and differential geometry sometimes, maybe, yes, next year in mathematical physics number 2. The last week is devoted to differential geometry of Lie groups, including these left invariant vector fields and so on. But here we restrict just to matrix groups. So for us, this construction is extremely important. That associative algebra as starting point matrix Lie algebra is the example. Construct this as commutator and use knowledge from 11.7 about concrete groups. I stress that this is not the only possibility, and I will show now how it works. That there is a well-known example of Lie algebra, actually, hopefully also well-known to you, because you should know it from my lecture of theoretical mechanics, or of course any secret study of books of theoretical mechanics, which you can do in addition to my lectures. And they are Poisson brackets. Theoretical mechanics. We introduced last year a so-called Poisson bracket, which is given by a strange-looking formula. So the first term like that, they are functions of Q's and P's, that is from the phase space. So functions on phase space were last year studied a little bit, and we discovered that if you define such operation of these functions on phase space, it makes some sense there. It is somehow motivated, because otherwise it looks weird that what is it, why? But there is some motivation for it, and it was used last year. And now we can have a look on this guy from another point of view, that this is an example of a Lie algebra. Lie algebra commutator. Yes. So, first of all, functions, if it is true that it should be a Lie algebra, it should be a vector space first, and there should be a linear combination. But it is just the example number one, that we have linear combinations of functions anywhere, including phase space. So this part is trivial. What is non-trivial now? Where is the commutator? And the answer is, try this guy and check that it is a good candidate, which will be successful at the end. So, is it skew symmetric? Yes, because it is some structure like that, not completely that, but because it is not a multiplication. It is some derivatives and then opposite term and so on. Is it bilinear? Have a look and you'll see that it is bilinear. If you have f1 plus lambda f2, put it to this expression and you easily see that it is bilinear. Yes. Of course, as usual, the biggest problem always is with Jacobi identity. And I believe that I mentioned it on the lecture. The Jacobi identity holds. It is not very pleasant computation to prove it, but it is brute force direct computation. Of course, there are also some more intelligent way how to prove it, but we didn't need them. By brute force, it is maybe 1 or 2 minutes, yes, of computation to check that really this kind of identity is true for this expression. So this is another example of Lie algebra. What is interesting on it? First of all, it is infinite dimensional example, yes, because the linear space of functions on manifolds is an infinite dimensional linear space. And the second, maybe even more interesting point of this example is that it is not constructed in this way. It is a nice example that this is not everything in Lie algebra. in Lie algebra theory, that there is no AB in this, because if you use some FG, just as I mentioned before, this kind of bracket is not FG minus GF because it is 0. Yes? This is something much more complicated done with these functions, which still has these nice properties. So really, it is important example of Lie algebras, which is not constructed in this way, because it is some idea in majority heads that Lie algebras are always done like that. Not always. Sometimes the commutator can be given by more complicated formula, something like that. So remember that, yes, often it is constructed in this way, but not always. And there are also interesting constructions which are not of this type. Poisson brackets is an important structure. Okay, so now by this example, we have a lot of examples actually, because we have these matrices as associative algebra, and there is a lot of interesting types of matrices, which give separately various Lie algebras. We will see it in detail. It is this point 11.7 where is a big table that the type of Lie algebras, some summation that compute everything. I will show you some examples how to compute some lines from this table. And there are several, maybe 10 interesting Lie algebras for physics and mathematics of this type, of matrix type. Now, something general. So we already know the definition. We already see several examples. So we see that we are speaking about something non-empty. And now some details that whenever you have the algebra, what you should do or what you should know, some basics. First, Lie algebra is a linear space, so you can introduce a basis and write it in this way, that decompose any element with respect to some basis. Now we think that this Lie algebra is finite dimensional. So it is not example very much of these Poisson brackets, for example, but of majority of our real examples. So how we compute the commutator then? Here we have xi, ei, yj, ej, which by bilinearity can be rewritten to this expression. So in order to compute the commutator for two general elements, you first need to know the components of these general elements, and then you should know the result of this. Now, what is this? It is a commutator of special elements, it's basis. But commutator of two elements of Lie algebra always gives you a third element of the Lie algebra. So also this element, this is some element in Lie algebra. And because it is in Lie algebra, it can be again decomposed with respect to the basis. Yes, so it should be something with k, ek, because it is an element of Lie algebra. And what is this something? It is k component of this commutator. So here nothing extremely wise is said. It is trivial. Now, what is this? It is a number for each k and each I and each j, because this is a vector and it is kth component. So it is a set of numbers which is usually denoted like that. So the result, and because they are numbers, you can rearrange them. Here are numbers, and here is basis element of the result. Basis element. So these numbers are really important. Actually, they enable you to compute the commutator, which is the basis of Lie algebra. Basis of Lie algebra that you should have some linear space. Okay, you know about this linear space. You know you find some basis. And now this is the second important step to characterize concretely algebra, that how the commutator is computed. And we see that how the commutator is computed is given by these numbers, this set of 3 index numbers. They are called how they are called Lie algebra. It has commutation constants, not commutation constants. How they are called, do you know? No? Well, some constants, I will. And they fully characterize the Lie algebra with respect to the basis. And that's why you need to know them. For each Lie algebra, finite dimensional, you should find the basis and then compute it commutator of anybody with anybody. Of course, in practice, because this is antisymmetric, so it is antisymmetric, structure constants. Okay, structure. So to compute structure constants with respect to a basis is something which you should know how it is done in practice, I mean. Now, this constants is a little bit misleading. It is okay, but it can be misleading that they are not. They are constants in the sense that they are numbers. They are not functions. By the way, there exist some similarly looking objects on manifolds, which also are denoted in this, and they are functions on manifolds. They are components of something. But here we are in the theory of finite dimensional linear Lie algebras, and then they are simply numbers. So the constant means that numbers, but they are not constant in the sense that they are the same in each basis. They are constants depending on the basis. So it is something like these constants. Yes, these are components of this vector, which are of course constants, and usually we are not saying that they are constants components, yes, or something like that. We say that just components, and it is known that they are depending on the basis. They are always related to some basis. So also these constants are related to the basis, and now you can compute easily that first in this basis our structure constants are given by this equation. In some prime basis, you first of all should know the relation that the prime basis as a function of cold basis. Yes, it is transformation matrix, which we used quite a lot when we studied tensors. Yes, this matrix. And here you obtain by definition primed constants and primed bases. And now, if you insert, I will not do it, but do it yourself, that insert these expressions inside the Lie bracket here. Now, recall that they are constants. You have a linear combination here and here. So because it is bilinear, put these constants away. Now, of course, use this decomposition also here. So you have 3 A's, here 1 A from here second and third A in this expression, and then use this. Because inside, what you will have is only non-primed E. Yes? So do this simple computation. It is best for you to do it yourself, not to have a look how it done trivial operation here on the blackboard. And you can compute the relation of these two guys. That you will obtain a formula that this primed thing is some 3 A's and ijk, say alpha, beta, gamma, here some alpha, beta, here perhaps gamma, but some of these matrices are inverse matrices actually. Yes? Compute which one. There are several A's, several A's to minus 1. The indices are like that. Here should be some I, J, K, but it is not good formula now because there is omitted which one is inverse actually. A's and A inverse here. I don't write explicitly. Do it yourself and then check that what is the suspicion that there is something which has 2 lower indices and 1 upper indices. Whenever we see something like that, after the first week of this course, we should have some suspicion that maybe it is something, and what, namely? Yes, maybe they are components of tensor of type 1, 2, yes? If it is true, there is some formula. If it is a tensor, it should be some formula. And check that this is exactly this formula. Yes? So, what we see that these are components of a 1, 2 tensor in vector space of this Lie algebra. So because we know already what is a tensor, we just learned that here is some tensor. How this tensor looks like? As usual, it should be like that. If you know components and if you know the basis, you compute the dual basis and glue it to components in standard way, and this is some C. So C is from tensors of type 1, 2 in the vector space of the Lie algebra. So the lesson is that in order to define this bracket, it is practically, it can be regarded as the definition of the bracket is the definition of some tensor of type 1, 2, which is not very deep statement because this is a bilinear product. It always is like that. But what should be a bit more interesting that how this tensor actually acts on 2 vectors and 1 covector, or some x, y, and alpha. If it is tensor of type 2, 1, 1, 2, it should eat two vectors and one covector and give you a number. And you can check that it is given by formula that do the commutator and insert it to alpha. Now, if somebody comes and tells me that I invented this tensor, I can check whether he is right, whether he really invented a tensor in Lie algebra. The only question is now, is it linear in x, linear in y, and linear in alpha? Linear in alpha is trivial completely. Linear in x. This commutator is bilinear, so it is also linear in x. Then the right slot in these brackets, in this canonical pairing, is linear. That's why it is linear in x. Not as easily like alpha one step more, but still quite simple. Why the same story? So we already see that if we have linear algebra, including the structure of commutator, we can assign a tensor to this linear algebra by this prescription. And now check that if you do it, it is more or less visible that if you introduce this particular tensor, it is this tensor which has just structure constants as components. Yes. So this is something like abstract definition of this Lie bracket using some tensor. Now, in practice, how many structure components you should really compute? Recall that this tensor has the property that it is skew symmetric with respect to xy because of the commutator. So it is reflected that its components are antisymmetric. And this, of course, makes the number of independent components much lower. So forget about this k. It is just a matrix. Yes, without this k, it is just a skew-symmetric matrix. If you have a skew-symmetric matrix, you just need this part of this matrix to know, yes, because this part is minus this. And here are zeros. But it is also this k independent. So here, if this is n by n matrix, this number here is the number of elements here is n times n minus 1 over 2. It's easily computed. So this is because of ij. And then for each ij, you have still multiplication by n because n possibilities in k. So here are n times n minus 1 over 2 times n, altogether real numbers to be specified for each n-dimensional Lie algebra. Well, what is the situation, for example, if we have just two-dimensional Lie algebra? We have E1, E2, then the structure constants are computed from the formula with ij. But now, if ij has only two possibilities, so there are four possibilities: 1, 1, 1, 2, 2, 1, and 2, 2 to compute this. But 1, 1 is not necessary because it is antisymmetric. So for 1, 1 you get 0, always. 2, 2 is not needed because of the same argument. And these two guys are minus with respect to another. So what is quite enough is just compute this. If you know the answer to E1, E2, you know everything. C1, 2, and here you have still kk, but it is now just two possibilities, 1 and 2. So what you need really is this and this, just two numbers. I hope that it is consistent with this formula for n equal 2. Yes, so realize that in small dimensional algebras you have just several numbers, not so big as it looks. In two-dimensional, just 2. In three-dimensional, you can compute. How much is it from this formula? Also a small number. So do not forget about that when you will compute some structure constant for small dimensional algebras. Do not compute things which are not necessary. Well, maybe this is all what we need from the general situation. Maybe if I forgot something, I will add it later on. And now I think that we are already prepared to go to Lie groups and to find some construction, how you can compute some Lie algebra for any matrix Lie group. So Lie group is not a linear space, it is a manifold. So it is a potato, not like that. This is a linear space and this is a manifold on pictures. Now, because it is not only a manifold but also a group, there is somewhere unit element. And I will directly call it as a unit matrix because we speak of matrix Lie groups alone, no more complicated. So all our Lie groups will be on this course just matrix Lie groups. So that's why the unit element is just a unit matrix. And now think of curves. We know what is a curve on manifold already. Yes, we defined it. Well, think of any smooth curve on manifold G, on the Lie group, which has this property that at time 0 it is at unit element. It also came from somewhere, yes, so it is not necessarily true that it is nothing before unit element. So in negative time it is somewhere here, and in positive time it is here, and in time 0, at time 0 it is exactly here. Now, very interesting object turns out to be the derivative of this curve computed at 0. What I mean that the curve, the component, actually the coordinate expression of the curve is 1t, 1nt, and 1t and an nt. Do you remember that when we spoke of curves on manifold, curve is an abstract thing, a mapping from R to a manifold, and there is a coordinate presentation. When you have local coordinates on manifold, the curve is expressed as coordinates dependent on time. So here, if we treat this Lie group as an abstract thing, then actually we always have this expression because only we treat matrix Lie groups. So matrix Lie group always look like that. So if the group element depends on T, it means that these matrix elements depend on T. Now, by definition, time derivative or derivative with respect to this T means that make this derivative with any element, and here that express it at time 0. So it is completely trivial operation, yes? The two dots in 0 always. And now, what is it? It is a constant n by n matrix. Here is a matrix which depends on t, but when you make a derivative and evaluate it in 0, you obtain a constant matrix. Call it C. Constant n by n matrix. And this matrix turns out to be very interesting. Not only this matrix, but these matrices for any curve. This curve is any smooth. So there is not just one picture like that, but infinite number. You can have, for example, here some bt. Now what is interesting that the matrices, constant matrices n by n, they give you a associative algebra. Yes, they are just an example of associative algebra. So if you do some CD minus DC, where D is another matrix which comes from another from some B0 at 0 is, say, D, another constant n by n matrix, you can make this construction and you obtain a Lie algebra. Yet, at the first step, these two matrices already give you an associative algebra. But first, we do not see any meaning of computing neither the product nor the commutator with respect to the Lie group. But we can show that it has some meaning. First, try this curve. So take any two curves like that, and now introduce not C but what? AB, some A, T. This is a third curve. First curve, second curve, third curve. Now check that it is also the curve like the first two. That means, are they smooth and do they start at unity? So what is A0? It is a computation.
A0 and B0, they are both in matrices, so they will...
Exactly. Trivial computation, well, it is not hard computation, but it is very important computation. So it can be written or drawn somewhere like here. Yes? From these two curves, I somehow created a third curve. And now, what is its derivative in 0? So first, what is its derivative for any t? There is a multiplication of matrices. Think it over how this is done. And this is standard Leibniz. So A dot is A dot B, the first term of Leibniz, plus lambda A B dot. Why this lambda?
Because there is lambda t instead of t.
Yes, here is just lambda t. So when you make derivative with respect to t, there is a lambda. Now, what about computation in 0? A dot in 0 is called C. B in 0 is unit matrix. So it is C unit matrix plus lambda A in 0 is also unit matrix, and B dot 0 is D. So it is C plus lambda D. Why it is interesting, this computation? It showed us something quite interesting, which we didn't know. That how this CD came, that study any curve going from unit matrix to the Lie group. This is some Lie group. And, well, what is the interpretation? Can you give some interpretation in terms of mechanics? Standard, realize that this can be interpreted like some traveling in mechanics. This is something like some space in mechanics when points are moving, some configuration space of something, say, and something is going along this line. Now, what does it mean to compute A dot at 0 in mechanics? Initial velocity. So we can put some vector c here. Yes, it is initial velocity of this path. Well, here is this d. And what we now show that there exists a linear combination, that the structure of these velocities has a linear structure, that we study actually velocities at the initial point, and they can be linearly combined. Yes? In the sense that when you have two vectors there, any linear combination has the same meaning, that there exists a curve, namely this one, which has the same velocity c plus lambda d, that the linear combination has meaning in this context. It is not just do linear combination, but is the linear combination also initial velocity of some curve? Yes, it is. Is it the only curve which has this initial velocity? Of course not, because initial velocity doesn't know anything after this epsilon beginning. Yes, it is computing with the beginning of the story. So many curves have the same c, many curves has the same d, and many curves have the same linear combination. By the way, it is something to which we come maybe next week, or where I don't know, where we start of actually different vector fields and manifold. Week 6, we will study first differential geometry on manifolds, and we start with the concept of tangent space. What are vectors on manifolds? Here is an example already on this, which we will study next, that they are vectors on some manifold actually, but in a very simple context, because they are matrices. So this is the first discovery, that we can introduce initial velocities as a vector space. And then what is more surprising, that this vector space is naturally a Lie algebra, that if you compute this, it also makes sense. For that there exists a curve whose initial velocity is cd minus dc if some curve exists for c and some curve exists for d. It is not very pleasant to do it. I will write you the curve. You can check. A minus t maybe, and b minus t, but maybe it should be a to minus 1t. Actually, I don't remember, because it is not very interesting now. So what about this? Call this some bt. At t0, we have unit, 0. So this curve also starts in the unit matrix. It is multiplication of elements in Lie group, so the result is in Lie group. It goes if the Lie group are, for example, orthogonal matrices. So this is also orthogonal matrix. It is not more than, or it is not some non-orthogonal matrix. Yes? So this is inside the group, and it starts at unity. So it is another example of a nice curve when you have already two curves. Yes? And you can compute its dot at unit t, at 0t. And what is not very nice here, that you obtain, check it, that it is unit metric, it is only on the order of epsilon squared is something interesting. So it is some analytical, analytical problem, so to speak, which you have somehow discussed, that what does it mean? That you have at epsilon squared this CD minus DC somewhere. So the first derivative will give you 0, and only the second derivative will be interesting. It is not a problem which cannot be surmounted, but I will not go to this because of the existence of the alternative definition of Lie algebra, which is by the left invariant vector fields, where this problem doesn't exist. Yes? So this is a technical problem, in my opinion, a little bit technical problem when you restrict to matrices. Yes? This is the weak point of the, a little bit. It is not surmountable. It is surmountable. In many books, they show that how to treat it. But for us, I don't want to go to these details because it is not so interesting, but just to learn that there is a way to make it correctly. And the result is that not only linear combination can exist here or exist here, but also the commutator has a meaning. It is also initial velocity of some curve there. Yes. So we have both this and this in the linear space of initial velocities of curves on Lie group. And especially this one is fully dependent of the structure of the group. There are products in the group. So this guy somehow feels the structure of the group from which it is computed. Yes, because it is computed of some product, and the product is the structure of the group. So it may be not big surprise then that this structure, which is computed from the Lie group structure and gives you Lie algebra structure, gives you a Lie algebra which is interesting for you if you want to study this Lie group. Yes, some information from Lie group penetrates here from multiplication to some commutator of some things. And this means that the structure of Lie algebra somehow feels the structure of the Lie group. This is a very important point. That's why if you study this particular Lie algebra, the Lie algebra of these velocities in unit point, you study something which is first much easier than the Lie group because it is Lie algebra. It is linear algebra. This is Lie groups are Lie algebras is some part of linear algebra. Lie groups is some part of manifolds. And manifolds in general are more difficult than linear algebra. So if you want to study Lie groups directly, you study something complicated. If you first compute its Lie algebra by this method, you study something more easy. It turns out that much more easy. And in spite of that, very useful. So it is a very big discovery of Sophus Lie that he introduced this concept, because Lie algebra gives us a lot of information about Lie group, and it is much easier than to study directly Lie group. Yes? This is the interesting story. Sometimes you just need in physics, it's Lie algebra. Sometimes the group itself is not so interesting, but usually also the group is interesting, and Lie algebra is the first step to study this Lie group. That thorough study of Lie algebra gives you a lot of information about this Lie group, and sometimes even all information you need. So this is the reason why we want to study exactly this Lie algebra, and I will denote it that if you start from Lie group G, our Lie algebra will be denoted by these numbers. Sometimes, or quite often, it is also denoted by other type of letter. That this is some calligraphical font in, for example, in Tech. Sometimes it is some Gothic font used. So if you also study other books, you will often see Gothic font for Lie algebra and not this calligraphical font. And also notation, which is more or less standard, and also I use it, that, for example, start with GL and R. So this will be our G. Then our Lie algebra, which we compute, how it looks, will be denoted by small letters. Sometimes also Gothic or I don't know what, but I use standard letters, but capital letters and small letters as a distinction. Capital letters always mean that we are speaking of group, and small letters we are speaking of its Lie algebra. Yes, so this is still the same, that GL and R, but here is small, here is big, so we know that this is a group and this is a Lie algebra. And they are related. There is unique Lie algebra for given Lie group, and it is to be computed. Something like this method, not directly this, but more or less this one. So we can start, for example, in by this example, to compute this Lie algebra from this Lie group. So if our A, now imagine that this is GL and R. So all points on our curves should be in GL and R. That means that they should have determinant different than 0. Yes, there is some restriction. Not all matrices, it is not just a matrix curve, but matrix curve in the space of regular matrices. And now one small trick, that if you compute this and call it C, how the beginning of the curve looks like. It is A t is A0 plus A dot 0 t plus and so on. And for epsilon, it means 1 plus, here it is C, and t becomes epsilon. And here plus higher orders. So this is the beginning of the curve, always. It is a smooth curve. So now, for example, in this GL and R, it is nicely seen that, imagine that this curve should be regular, curve of regular matrices. So this should be a regular matrix as well. Now, it has the structure that unit matrix, which is clearly regular. It has determinant 1. It is very far from determinant 0. Yes, it is a leap from 0 to 1. And now, what should be the determinant of the whole guy? Why we compute it? Because if it is 0, it is not good. Yes? We should restrict to such C's that give us determinant non-zero from that. Yes? But determinant of a unit matrix plus epsilon c, it looks like 1 plus epsilon c11, here epsilon c1n, and so on. Imagine like that. And if you compute determinant, this determinant will be a series in epsilon. It is actually not infinite series, but a polynomial. There is a term without epsilon, there is a term with 1 epsilon, 2 epsilons, and so on. It depends on how big is the matrix. Terms, what is the term without epsilon? What is here without epsilon? If you compute the determinant of this matrix. Number 1. Then will be a term with epsilon of something. What is this something? Some product of some elements. Plus epsilon squared of something, and so on. And now the question is it dangerous, this expression? That means, does there exist a matrix C which produces 0 out of this expression? And the result is, of course, not, because it is a big number, 1, plus extremely small numbers. Yes? So 1 plus epsilon and something cannot be 0, because they are finite C's. So it is number 1 plus some finite number times epsilon. So, of course, in limit epsilon goes to 0, this is completely safe from the point of view that it never can happen that this is 0. What does it mean? That any C is good. Is it clear, this argument, that if you want to compute curves which have only non-zero elements, everywhere here is not non-zero, but regular, with determinant non-zero. So at the very beginning, the starting of this curve looks like that. Now, this C tells you that in which direction you go in this Lie group. It is the initial velocity. It can be in any direction, but it is in principle possible that if you go to bad direction, you turn to have determinant 0. Here it is determinant 1, but maybe in some bad direction the determinant will be bad. What is bad now? Only 0 is bad, nothing more. So is it possible to find such bad direction which gives you determinant 1 in the very neighboring point? This result says that not, because determinant is this expression, and this expression is completely safe from being 0, because it is 1, which is far from 0, plus epsilon, which goes to 0. So it is not dangerous, this expression, for any C. So this C is any n by n matrix. So these are matrices with the condition that determinant is not 0. Here are matrices with no additional condition. Any n by n matrix is the element of Lie algebra of this group. As I told, maybe you will somehow acknowledge this result only after seeing other results. This is not very typical. So from other results, it will be more clear for you. Typical is, for example, ON. Take ON. So now this is ON. What are matrices from ON? They have to have this property by definition. Now, all matrices at the curve should satisfy this. So we can write it that AT equals 1 for any t. And now compute d over dt in 0. And what you get? A dot 0 t times a 0 plus a 0 t a dot 0 should be 0 because on the right hand side we have no t. Now what is this? This is ct. Here is 1. Here is 1 t formally, and here is c. So we have ct plus c equal 0 or ct equal minus c. Yes? So there is a vector space of velocities, but velocities to such curve which are to ON, not to GLNR in general, are restricted somehow. There are good directions and bad direction. If you go in the direction phi, which doesn't fulfill this condition, in the first order of epsilon, you already will be in non-orthogonal part of the group, GLNR. Yes? If you want to remain in ON, including the very beginning, you should choose the direction C, which is given by skew symmetric matrices. Otherwise, you in the first order of epsilon already go in, you spoil this condition. In order to see it maybe better, is that there is another way. It looks another, but it is the same idea. How to compute the Lie algebra? Our method yet was that write down the equation which defines the group and apply d over dt in 0. And you see the conditions on C. But think that completely equivalent is write your A epsilon as 1 plus epsilon C and insert this in this equation. So what we get? 1 plus epsilon C t multiplied by 1 plus epsilon C should be 1. Yes? This is this equation written for epsilon plus writing that A epsilon is like that. Now compute. Transposition of sum of two matrices is transposition of both. So here should be T and here should be T. Unit matrix transposed is still unit matrix. So it is 1 plus epsilon psi T, Ct multiplied by 1 plus epsilon C. And what is it? First of all, 1. It is this one. Okay. Now plus something epsilon. And what is at epsilon? Ct plus C. And there is also something epsilon squared. Not important. We are computing everything to the first order epsilon. So what we see, that if this is not 0, we have a problem. We have at the first order of epsilon already a problem that that this equation is not satisfied. And now you can at home return to the first example that we have know this problem for GL and R. This problem comes for all other groups. So you see that the same condition is computed either by formally make d over dt in 0 or by simply make this ansatz in the definition equation always. And then compute what is at epsilon and put it 0. This is the whole mechanism. What about, for example, UN? What's the time? we have still 10 minutes, yes? GUN. What is the definition equation? A dagger A is unit matrix. Not just transposing, but transpose and complex conjugate. Hermitian conjugation, yes? So A, once again, 1 plus epsilon C. What is the condition on C in order to fulfill this equation to order epsilon? So A dagger is 1 dagger, which is 1, plus epsilon C dagger by or cross this. What is it? It is unit matrix plus epsilon something. Now what is this something? Epsilon terms are C dagger 1, which is C dagger, plus from here C, and plus epsilon squared. Not interesting, but remember that altogether it should be just 1. So there is bad term in order to epsilon, namely this is the bad term. But it can be put by hand to 0, and then it is not bad term. So what is the condition? This one. Do you know some name for such matrices? You are from third year, you know already something from quantum mechanics. And what is the name for this fact? In quantum mechanics, it is very important that what matrices have this property or operators. Did you have it already in quantum mechanics, this word or not? Okay. Did you have it in linear algebra? Such matrices? How they are called? Hermitian matrices. They are very important things in quantum mechanics. You will see. What is possible name then for this? Yes, anti-Hermitian. So they are complex matrices in general. Yes, because also these A's are complex, which are anti-Hermitian matrices. And now what we know already, and what we will check now, that if the general story was true, that those types of matrices, anti-symmetric and anti-Hermitian, should give us some Lie algebra. Yes, so we can check it directly. So I will do it for this ON. Yes, ON is anti-symmetric. And if we have UN, then small un, that means its Lie algebra, is anti-Hermitian. So we did already computation of Lie algebras for the most interesting Lie algebras, actually. Well, maybe special linear group is also interesting. I will do it if the time will be for me. But first, let's prove directly that somebody tells us that think of anti-symmetric algebras, anti-symmetric matrices n by n. My claim is that they give you a Lie algebra. Yes. So what should I check first? If so, my condition is I only study matrices which are anti-symmetric. Now I have 2 of them now, and the question is, linear combination is still anti-symmetric matrix. And second, again, I have 2 of them. I compute the commutator. And check whether the commutator is still antisymmetric, if C1 is and C2 is. So whether this is minus C1 and C2. Question mark, question mark. This is necessary to be checked, whether my friend told me true story or not very much true story, yes? That these matrices fulfill the conditions for Lie algebra. So if we know compute with this T a little bit, the first line is hopefully trivial. Yes, this is of course clear. But let's check the second line. If it is not clear, then of course think and make it clear. Now, number 2. C1, C2 minus C2, C1, because our commutator in matrix groups, matrix Lie algebras is always of this type. Yes, this is our commutator whenever we speak of matrix Lie algebras. So this is the commutator, this is transpose of this commutator. Now, there is a linear combination, the first minus second. What about T there? It goes here and here, yes? So it is C1, C2, T minus C2, C1, T. You should know how to work with transposition. Now, what about how transposition works on product? Everything can be somehow seen from indices. If you know that the product is this and linear combination is this, in indices you can derive these rules if you do not know them. Here it is product of transposes, but reversed. C2 transposed, C1 transposed, minus the same story here, C1 transposed, C2 transposed. Once again, if you don't know this step, don't understand, do it yourself through indices, that it is true. Now, both our matrices are from the Lie algebra, so they are antisymmetric. So here it is minus C2, here it is minus C1. Again, minus C1, minus C2. But scientists discovered under microscope that 2 minuses is plus. So here is what? C2, C1 minus C1, C2. And other scientists discovered that it is minus of C1, C2 minus C2, C1. And this is our commutator. So we say yes. Can you imagine the computation, the same computation for the next Lie algebra? Here will be dagger. Everywhere dagger instead of T. The same rules, check the same rules. And if the rules are the same, the result is the same. Now, what about Lie group just to begin? This Lie group, what is the corresponding Lie algebra? Here we have determinant of A should be exactly 1 by definition. If our A is unit plus epsilon C, then its determinant is 1 plus epsilon, and now we really need to know what is there. And maybe you remember, because I mentioned it at least in theoretical mechanics in one place. So do you remember what is here? what construction out of this C is here at the first order? It is the trace of the matrix. I did it, the computation at theoretical mechanics. Try just 2 by 2 matrices, 1 plus epsilon C11, epsilon C12, epsilon C21, 1 plus epsilon C22. Determinant, you will see that it is a trace. Then imagine you do 3 by 3. Again, you will obtain trace. And then imagine what about the general situation, and you come to conclusion that it is the trace. Yes. So what is the Lie algebra? Lie algebra double dot that trace of C equals 0 because we should have no term at epsilon. So this is the end. We will proceed next times. We will have some exercise when or this meeting when we will compute these Lie algebras and find the basis, for example, that what is the basis among antisymmetric matrices and so on. Yes? So thank you. This is the end.